Thank you for dialing in and listening to this Timber Design Society webinar on timber mid-rise and MDH, and in particular 3604 versus 3603 in terms of engineering design. A few things I want to cover off in here as we step through the presentation around connectors and fasteners. Obviously the updates to 3604 and the recent publication of a 1720.1 which replaces or will replace our NZS3603. My name's Daniel Scheibmair. I'm a engineer working for Simpson Strong-Tie. Have had a fair bit to do with Timber Design Society over the past years, and was also the TDS representative on the 3603 review committee, or the 1720.1 standards committee, and I sit on the 3604 review committee as the Engineering New Zealand representative. So before we get into the technical side, what I wanted to cover off quickly is different building typologies. Standalone housing obviously is fairly familiar to most people and fairly self-explanatory. Single detached buildings, typically 2 to 3 stories in height. The next step from there would be semi-detached and duplex dwellings, which are sort of townhouse type, but with only a couple of buildings side by side, and these are starting to become a little bit more predominant in some of the larger urban areas and subdivisions, similar in height to standalone dwellings. And then, as I said, the townhouses, which is an extension of the duplex buildings, where we've now got a whole lot of these essentially single dwellings, standalone dwellings, but connected by one wall, one to another. From there, it really gets into bigger buildings, so apartments, and the picture's slightly confusing, but the apartments normally self-contained units, if you want, within a larger building. So these two types of buildings in here, and then we have mid-rise and medium density. Now, mid-rise and medium density aren't defined in any documentation or regulation that we have in New Zealand, and not very well defined overseas either. Mid-rise typically is accepted as a 3 to 6 to 8 story in height, whereas medium density isn't necessarily so much the height, but it's the mix of buildings. So can be up to 3 stories or around that 3-story mark, but with multiple occupancies across the one building. So similar to apartments, but in a much smaller building. Now, why is all that important? Mid-rise and MDH obviously are starting to gain some traction in New Zealand, or we have for quite a few years now, and so we are starting to see these mixed use buildings, multi-tenancy buildings, and some of those are being built in timber rather than just steel and concrete. Key difference here between mid-rise and MDH, or particularly the MDH, is the vertical intertenancy. So where apartments obviously are generally split floor by floor, MDH quite often has a single tenancy that runs up the vertical. So you might have a unit that extends over 3 stories, and that is one tenancy, whereas obviously in apartments you would normally have each tenancy across the horizontal rather than across the vertical. So you've got vertical intertenancies, whereas MDH you've got horizontal intertenancies, but the tenancy in the vertical is the same. So quickly on standards changes, as most of you will be well familiar now, 3603 has been up for review or under review for quite some time now. The intention was to align it more closely with 1720.1. And that has happened. So what we've ended up with is an appendix that modifies 1720.1 as the basis. Slightly convoluted process in that it doesn't actually modify 1720.1, which is an Australian standard, and instead has an appendix, as I said, so separate document, which is the document on the right hand side there, which provides clauses that modify the different sections of AS 1720.1, and hopefully that will change once Australia reviews their 1720.1, so that we actually get a joint Australian and New Zealand standard. At this stage, 3603 is still acceptable to use, and there's a transition period of 1 year. So there's another 1 year before 1720.1, or the NZS AS 1720.1 must be used. Up until then, 3603 can still be used. 3604 This is currently under review. Largely corrections. There are some additions and improvements that have been scoped, and I'll talk a little bit in a little bit more detail about that in a minute. But this is obviously standalone dwellings, or the primary focus for 3604 has been standalone dwellings, residential housing, which is now being pushed into multi-storey. And so there was a scoping exercise that was done in 2019, 2020. And that scoping defined what the review of 3604 was going to cover. And that includes, as what's on the screen here, solutions for improved thermal performance. So that's one of the bigger ones. Foundations, obviously, with the earthquakes, steel bracing elements for wide openings. And that at the moment is looking unlikely to actually be included in the review, but nonetheless it was scoped to be included, so has had a good look at. Long span beams and lintels, framing around internal stairwells, and then there's a little bit on internal masonry walls. And the big one really for this presentation is 3-storey multi-tenancy buildings. So there is a push to get 3604 to have a better look at how it can support the uptake of medium density housing in New Zealand. And then the last one, corrections, is fairly self-explanatory. Obviously there's a fair few items that just need to be tidied up and corrected. So the 3-storey multi-tenancy, initially it was called Part 2, or it was looking like it was going to be a Part 2. That is now likely to be included to some extent within the actual 3604 document. So there is no Part 1, Part 2, but at the scoping stage, there was some limits that were looked at, and again, the limits are up on the screen for you to see. These limits are fairly prohibitive in terms of what you might get. So you're going to get some standard box shape 3-storey or up to 3-storey buildings, multi-tenancy buildings, but really there probably still be a reasonable proportion of multi-tenancy design that will need to be done as specific engineering design rather than out of 3604. Probably not much to talk about in detail. And here, as I said, the information is on the screen in terms of the limitations, but that they are obviously quite, there's quite a lot of them. So 3604 versus 3603, most of you again will be most familiar with the fact that 3604 is an acceptable solution. Acceptable solutions are by their nature rather prescriptive, and they also have a rather restrictive scope, and that I already highlighted in terms of the 3-storey. So there'd be a whole lot of limitations around where 3604 can be used for multi-residential design, MDH design, and the approach obviously is very prescriptive. Compare that to 3603, which is timber engineering design standard, so specific engineering design, and as I've already talked about, 3603 is really out of date, in that it has now been, or not replaced, because you've got this overlap transition period, but it's essentially being replaced by NZS3606 and a big part of that makes sense, because for larger timber buildings, whether it's commercial, industrial, or multi-residential, 3603 doesn't really capture the design methodology that is best practice, or that's used by engineers already, and it doesn't align with current products, particularly for larger timber buildings. So NZS 1720.1 uses 1720.1 as the basis, and then modifies that, and so there's a simplified and a detailed design method. That's the simplified method is essentially 1720.1, and then the detailed design method provides more information, particularly around fasteners, for design of larger timber buildings, and that uses the European yield model, so the EYM. So talk about fasteners first in terms of 3603 design. The EYM looks at the different failure modes. And then from that you get a capacity for your fastener. Obviously you can do that for 2-member joints, so where you've got single shear, and 3-member configuration where you've got the fastener and double shear joints. You get different failure mechanisms, or potential failure mechanisms, depending on your design parameters, spacings, etc., screw diameters, timber properties, all those sort of things. You get potentially different failure mechanisms, and so you work through calculating or checking each of those failure mechanisms, and obviously the lowest one will be your governing design, and give you the strength for your joint. Now, what's important here to just highlight too is the fasteners and material properties for those fasteners. Obviously, the fasteners will need different material properties to plug into these calculations to what we've seen in the past in 3603. And one of the things that the committee had a look at, and this is a learning from our concrete standard 3101, where there's an inclusion as an actual clause that says the mechanical and chemical anchors used in concrete or used with concrete must have a European technical approvals. So that does limit or restrict certain products in the New Zealand market where they aren't supplied out of Europe and therefore haven't got European technical approvals. And so this information around material properties for fasteners in the timber standard was quite specifically added as a commentary clause, so that it doesn't exclude screws or suppliers that aren't from Europe, but nonetheless it draws attention to the fact that you do need to have these design parameters, and they should really be stated in declarations of performance or European technical approvals, those sort of pieces of information, and it shows what the different material properties are that you need for fasteners. So connectors then, as per 3603 or the new NZS AS1720.1, and this is where it gets a little bit more complicated. Fasteners, as I said, are fairly straightforward because we've got the detailed design method or quite prescriptive approaches in terms of 3603, in terms of screw diameters and spacing. When it comes to connectors, it gets a little bit more complicated. So 3603 already had a clause in the back and an appendix that talked about AS1649, an Australian standard that looks at testing connectors and coming up with characteristic capacities. And there were some minor modifications that were made in 3603. NZS AS1720.1 now refers directly back to AS1649. But what AS1649 does is it looks at an LPL or a lower, as it says in brackets, a fifth percentile value of your test data. So you run a number of tests on the same connector. You determine a load capacity from that as a fifth percentile value with 75% confidence. You then have a look at working out your ULL or your unit lateral load, which is as per the two formulas on the screen here. So one's a fifth percentile and the other one's an average load. So this is the LPL. And then from that, you take your basic working load, which is the lower of these two numbers that you've calculated. And then you look at your failure, whether it's a failure in timber or a failure in metal, and these two different factors that you use to multiply your basic working load to get a characteristic load. What we do as Simpson Strong-Tie is then have a second and third look at these test results or at the capacities that we've arrived at. So the first one that we add to it is essentially serviceability load, deflection governed. So we take the test results and have a look at a joint slip limit, and typically this is 3.2 millimeters, unless it's for hold down connectors where we allow up to 6.4, and that's because they're generally larger connectors than your general connectors, joist hangers, etc. And where joint slip is a little bit tighter because of the thinner material. So the third part then is theoretical calculation. So we run through and calculate the actual capacity of the fastener, so the screws or nails into the timber, and make sure that if that governs, then we limit the capacity based on the calculations. And so what you get, as I said, is these three different results. The first is your AS1649 characteristic capacity. The second one is a serviceability aspect, and then the third one is the actual calculation checker run over the top, and the lowest will obviously govern. And so you'll find that for the DTT2, which is shown in the picture here, we published a capacity of 7.7 kilonewtons. Sorry, and I should also say that's the design capacity, so it's already got the 5 factor and the load duration factor built into it. Obviously, we're looking at uplift here, so load duration factor of 1. So that 11.03 kilonewtons times 0.7 times 1 is 7.7, which is what you find in our literature. So that's if you went through and did it as per 3603 or as per 1720.1. If we now have a look at 3604, 3604 in clause 2.4.7 talks about a connector capacity, and within that it refers to brands EM1. So the actual design capacity here has a characteristic value, and that characteristic value is obtained by testing in accordance with Brand's evaluation method EM1. So what does EM1 look like? Well, EM1 is essentially our LPL, our initial test data, 5th percentile with 75% confidence. So we take our test results and simply analyze our test results to come up with a lower probable load, above which we know that 95% of results should sit. And so when we take again that DTT2 and we analyze that data as simple calculations, we get a characteristic load of 17.3 kilonewtons as Brand's EM1 calculated. And that, as I said, is very similar to the LPL that we use in 1649, but obviously is very different to the characteristic load that we get out of 3603 away 1649 by the time we've applied the other factors to it, the ULL, and applied the design working load reduction factor based on the failure mechanism. And that's so this LPL, and as I so the LPL is simply test data. The 3603 characteristic load, as I said before, for the numbers that we publish, as in Simpson publish, that could also be limited by the joint slip or the theoretical calculations rather than just AS 1649. But that gives you an idea of the difference between the actual characteristic capacities, depending on whether you've calculated them based on 3604, i.e. Brand's EM1, or based on 3603, i.e. AS 1649. And so hence in our tables, you'll now see in our 3604 catalogue, we publish a capacity for the DTT2 of 17.3 kilonewtons, which is quite different to 7.7. Granted that this is characteristic, so it still needs to have the variability 5-factor applied to it. So what that means is that really 3604 characteristic capacities aren't equal to 3603 characteristic capacities. So it's not just the additional joint slip limit that we apply, that as in Simpson apply over the top, or the theoretical calculations that Simpson applies over the top, but even just taking the actual calculations, comparing Brand's EM1 to AS 1649, you do get different characteristic capacities. And so therefore you should really be using specifically developed data that is assessed as per AS 1649 for anything that's designed to 3603 or to NZS AS 1720.1, and the information that's been analysed as per Brand's EM1 is really only applicable to 3604 type structures, so anything that's within the general scope in terms of building within 3604. And a second note here is really same sort of thing, that if you take the 3604 characteristic capacities, so if you take something that's been analysed as per Brand's EM1 and you apply your phi and K1 factor, you're not going to get the same result as what you would if you've done an analysis as per 1649. And particularly for us as in Simpson, you won't have the serviceability aspect or the theoretical calculations applied for the capacities that are in our 3604 catalogue. So just a quick recap, obviously, if the numbers that we've calculated or the capacities that we publish in our 3604 characteristic catalogue are only applicable to 3604 type buildings. What are these buildings? And this is only a high level summary, but importance level 1 and 2 buildings. At the moment, current height of 10 metres, 3 stories only if it's 2-storey, with a part story in the roof, so not full 3-storey plus roof. And the floor area not exceeding 250 square metres for a 3-storey construction. And as we've already said before, this is obviously currently under review, and there will be some additional scope in there for 3-storey, which will expand on that slightly, but nonetheless it won't cover, and I had that up on the screen before, it won't cover a lot of probably the 3-storey designs that we are seeing being designed and built in timber, concrete or steel at the moment. So that's the first part of the presentation, and really focusing on the difference between 3604 and 3603 in terms of determining characteristic capacity and why it's important to use the correct numbers. The next part I want to look at is bracing. 3604 type structures, so light timber frame buildings that we're well familiar with in terms of residential design, obviously use framing, light timber framing with some sort of sheathing on it, whether that's plasterboard, plywood, any other sheathing that gets fixed to the framing behind it to provide the lateral restraint to our buildings. Now the elements within that bracing panel are obviously the framing behind it, the sheathing on the top, then you've got fasteners that tie the sheathing back to the framing, and then you've got a compression stud that bears down onto your foundation, and at the other end you've got a hold down connector to take care of the tensile load in your brace panel and ties that down into the foundation. Now 3604, similar to what we talked about with the connectors, 3604 and a lot of the products in the market that have been traditionally designed as hold down connectors for these brace panels don't really give consideration to any stiffness or movement in that panel, but simply look at the actual load capacity, so the strength aspect, but not necessarily the stiffness. So obviously when we translate that design method or that construction method into multi-storey, we want to be looking at stiffness as well as strength. And so multiplying each of these brace panels over several levels, over several stories, if we get a certain amount of movement due to the stiffness of the connector and the stiffness of the panel, but we're primarily looking here now at the connector because that's what the talk focuses on, that movement, that deflection of our connector of the brace panel obviously has an impact on the rotation of the panel, and if you have that in multi-storey design, because you accumulate each of these deflections or movements, you do end up with an overall building movement that can be quite considerable, and 3604 doesn't really deal with that because 3604 only obviously deals with single story type buildings or two-story up to two-story buildings. So that the primary aspects that 3604 looks at when it comes to bracing is really distortion of the building, so the stiffness of the panel itself, to make sure that we get a building that remains rigid enough and doesn't start to lean over, but that has not a huge impact on the connector, as I said, the hold down connector. And then we have fixings at the bottom of our building to make sure that the entire building doesn't slide along. And these aren't necessarily part of the bracing panel, but these are hold down bolts, bottom plate fixings that normally tie our building back down onto the foundation to stop it from sliding along. Now, both of these aspects do apply in MDH buildings too, 3-story plus, but there are other aspects that come into play when you get into taller buildings, and one of those is overturning of the actual building, and obviously what's shown here is a little bit extreme in that it is a very tall tower, but nonetheless the overturning needs to be considered. And as I've already touched on, there's elements of brace panels in terms of deformation and movement, the stiffness, flexure of these brace panels at each floor level, that when you accumulate those over several stories have quite a different effect on the building than what is acceptable in a 3604 type structure. So when it comes to MDH or mid-rise, light timber frame obviously is still an option in terms of designing, and I'll talk about the different mass timber and other options, timber options, at the end of the presentation. But light timber frame as a cost-effective solution here. The biggest issue really is, or not issue, but one area that we need to consider is stiffness as well as strength. And so when it comes to hold down connectors, which potentially you can still do because there are connectors on the market, and Simpson has got some heavy duty connectors, as do others, you need to look at the actual stiffness of that connector as well as the strength of that connector, so that you actually get your overall building stiffness and flexure design correct. The other option is to use an anchor tie down system, and this is essentially the same principle as traditional hold down panels, and they've been talked about for quite some time now in the New Zealand market too. So I talked about anchor tie down systems probably 3 years ago, 2.5, 3 years ago at a TDS roadshow in greater detail. But the concept in terms of the brace panel remains the same. You've got light timber framing, you've got some sheathing across the top of it that has fasteners to tie the sheathing back into your wall framing. You still have a compression end of your panel and a tension end of your panel, but instead of having this hold down connector that sits in the bottom corner of your brace panel, we now run a rod up the length of the panel and then provide a tie off at the top plate level. So you've got a rod, and I'll talk about these take-up devices in a minute, but you've got a steel rod that runs up your brace panel until it gets to the top plate level, where you've then got a washer and a take-up device or a tie off to grab the top of the panel, so that as that panel wants to lift up, it pushes against the framing, pushes against the bearing plate, which pushes against the nut or the take-up device and then nut, and stops that panel from rotating up and transfers that load into tension. And that rod is connected into our foundation to pick up the tensile load. And so if we do that over multiple levels, that rod, the steel rod, runs continuous over each of these levels. And if I go back to the previous picture, you'll see in here we've got these couplers. So the rod isn't, while we talk about a continuous rod, obviously the rod isn't full length over multiple stories, but these couplers that allow you to join one rod to another, and potentially a larger rod to a smaller rod as well. So over several stories, we have this continuous steel rod that runs up, and then at each floor level, at each top plate level, we would tie off to provide the tensile or the tension hold down for that brace panel below it. Now, in reality, because it's quite hard to actually get devices, take-up devices, and I'll come to those, and the tie-off happening at top plate level, because that sits within the mid-floor, we actually do it at bottom plate level of the next story up. And so this is where people get slightly confused, or potentially get confused, because you've now got a tie-off at bottom plate level here, but it's not for this brace panel in here. So it's not like our traditional hold down connector, just because it sits at the bottom plate level here, that it's for this panel. The tie off is actually for the brace panel below it. And so then your next level would have a tie off at the bottom plate level of the next story up. Once you get to the top of the building, then obviously you have a tie off at the actual top plate level. As far as the design's concerned, as I said, the method is exactly the same. Your tensile load comes down through your steel rod, and you've got studs that act as your compression stud pack. What's important here to note is that the lever arm between tension and compression obviously is now changed, because as you go down the building, your loads accumulate, and so therefore you get larger tensile and compressive loads, and so you end up with reasonable, or potentially reasonable number of studs in here to transfer your compression load, and the center of your stud pack that provides the distance to the center of your rod, as far as the lever arm is concerned, between tension and compression. And so just be careful when you're designing these that your compression isn't the center of the rod, it is obviously the center of your stud pack. So then when it comes to tie off, as I've said, you've got this continuous rod that runs up the building. We're tying off at top plate level in theory. In reality, we're tying off at the bottom plate level of the next level up, because it's a lot easier to get the components into there. If we put a bearing plate or washer in here with a nut over the top, as the building settles, as we get shrinkage over each of these levels, particularly towards the top now, because obviously you get accumulation of shrinkage from each level, and so the top of the building is going to settle a whole lot more than the bottom of the building. We'd end up with a gap developing between the nut and the bearing plate, and so there's take-up devices that we put in here to deal with that settlement. And we have two different take-up devices. One's a ratcheting take-up device. This is a cut nut insert in here, so there's a threaded insert in here that is in 4 sections with a spring around the outside, and that grabs the rod as it comes through. Has these little lugs screwed through our bearing plate, because we're talking about the load pushing up against the bearing plate, pushing up against the take-up device, and that then grabs the rod. So this holds tight against the rod, so that the rod can't pull through in the downwards direction, so they can pick up the tensile load, but it can push through in the upward direction. And so the spring around the outside here allows the threaded rod, or the threads on the rod, to click through in an upwards direction, so that as the building settles, and because the device is held screwed to the top plate as the building settles, as the framing moves downwards, it simply clicks along and ratchets along, allowing the rod to travel upwards, and therefore any shrinkage that happens is removed because the device ratchets down along the rod. Now, the other take-up device that we have, and the one that we suggest people use in the lower stories, and that's around failure mechanism, is our what I call screw jack type devices. So these are two tubes. This one's turned upside down because it's a little bit easier to see, but it's the same device, just looking at the bottom of it. But you can see an inner tube here and an outer tube. That outer tube has a thread on the inside. The inner tube has a thread on the outside. And then you've got a spring around the outside, which is a torsional spring. And when you pull this activation pin out, that allows the spring to then unwind the inner tube from the outer tube. And so that expands it because as it unwinds, obviously because of the threads, it extends and therefore fills the gap in here. So quite different to the ratcheting take-up devices, and you now have a bearing plate with a washer over the top with this take-up device between it. Once you pull the pin out, if the building settles, the framing obviously moves down, and the torsional spring wound around the device would then cause that device to unscrew. Failure mechanism of these is quite different because you've got the rod running through the middle of it. The rod's in tension. The actual device is in compression because it sits between this bearing plate and the washer over the top. But because you've got the rod running through the middle of it in tension, that restrains it so it can't buckle. And you've got much coarser threads on here. So the failure mechanism of these is much more ductile, whereas the failure mechanism in your ratcheting take-up devices obviously is a lot more brittle or instantaneous, because once you've damaged the threads, you're going to lose your load carrying ability altogether, whereas this in here is going to take a lot more to deform those threads. Even if you do deform completely or an overload of that device, we are dealing with earthquakes here, so if you get a larger earthquake than you predicted, you're going to end up with the thread potentially damaged, but the two tubes would still then be compressed back to the original height, and you still end up with load path through here. You're still able to transfer some load through here. Obviously, you're going to get a bit more movement in it because you've now got a gap in here, but your load path nonetheless remains intact. And then in terms of tie-off, as I said, at top plate level, quite often if there's limited roof space over the top of here, or if it's quite hard to get into here, there is a detail that provides for a block to be installed. Obviously, that needs to be a reasonable way up the wall. And then that bridge block can have your bearing plate and take-up device over the top of it. So it doesn't necessarily have to sit at top plate level for the uppermost story. Now there's a little video here that's available on YouTube too, and I'll play that quickly. Now, this is from a test that was done in 2009 with the strong rod system in Japan on a shake table. I'll stop it here, sorry, because the video seems to have a little bit of a twitch on it. But as I said, the video is available on YouTube. So if you search for NEESWood, NEESWood on YouTube, you'll find it there too. But it is this was done in 2009, as I said at the start. And so this isn't really new technology. Globally, the anchor tie-down systems have been used quite widely now. And we have a much better understanding of the design principles behind it, and obviously refined the system from what it was back in 2009, or the components in that system that we had in 2009. So this isn't really new. It is a reasonably new addition to New Zealand, but it does enable light timber frame to be used in these multi-storey buildings, and overseas it's not just 3 to 6, but up to 8-storey, where we're seeing these anchor tie-down systems. And that leads me on to the next thing, which is really the use of timber, the effective use of timber. So obviously this is for light timber frame. So light timber frame uses stress graded structural timber, exactly the same as what we do in 3604. We can turn timber into other materials, as I'm pretty sure most of you are well familiar with. So there's glue laminated timber, there's cross laminated timber, and there's laminated veneer lumber, among a few others, but those are the primary for structural timber materials that are readily available in the New Zealand market. And so why do I want to talk about that? Well, those different materials obviously have, as you go from stress graded glue lam, cross lam, and LVL, as you go from one end to the other, you end up with much greater strength and stiffness in that panel, and some of the strength is a natural byproduct because of the randomizing of defects. The stiffness obviously is an impact of the actual engineering that goes into it. And so as we go from sawn timber, that's stress graded, to glue lam, and then onto CLT and onto LVL, there's much greater processing required at each of those steps as you step down through those products. And that is because we're separating the timber fibre a lot more and then reconstituting that timber fibre to give us the material properties and the sizes that we want. And that's where the stiffness really comes from. So because we can select different veneers when it comes to glue lam or cross laminated timber and laminate veneer lumber, we can impact the stiffness. As I said, the strength is almost a byproduct essentially of the randomizing of defects, which has a large impact on strength. As we go through those materials, the material properties also become a lot more consistent, or the spread of material properties becomes a lot more consistent. So you get much more uniform performance out of LVL because it's obviously veneers, selective veneers glued together, similar with CLT and glue lam. Stress graded timber obviously has a much greater variability in it because we're taking a log and just cutting it up and putting it through a stress grader rather than separating that out or dividing the fibers up even further and then rebuilding the different veneers to give the end product that we want. The downside of that is cost. So obviously light timber frame, if we take a stick of timber, the cost of that is much cheaper because there's less processing that goes into it than the cost of CLT or LVL. But we can't go or that there are limitations when it comes to light timber frame and the material properties. And so really, I wanted to throw this in there because I think it's important for us as engineers to just remember what the benefits really are of different materials and using the materials in an effective manner, so that the end user, whether that's the actual occupier or the developer, actually gets best bang for buck when it comes to their timber building, because that's the only way that we're going to encourage much greater uptake of use in timber in these mid-rise buildings than the steel or concrete that we're currently seeing. So skipping through a couple of quick examples of buildings that have been built. Stonefields in Auckland, there's a couple of big blocks in here, 3-storey, that were one of the first buildings in New Zealand that had the rod system in it, and that goes back quite a few years now. Mary Potter obviously has been talked about quite a bit over the past years. Again, this was designed with a Simpson Strong-Rod anchor tie-down system in it, and there's been plenty of talk around that. And now we're seeing probably a little bit more evolution of this, and Kaingaroa, a good example of that, in terms of using the right material in the right applications. So this is CLT, or we've done a few designs now with engineers have done a few designs using our system where they've used CLT for the stairwells and CLT floors, and then used light timber frame with the anchor tie-down system for bracing on each floor level. And even the system itself has had a little bit of refinement by engineers that have used it. This is a couple of pictures from the Kaingaroa project, but we do, as in Simpson, provide cast in anchors or threaded rods with washers attached to them that get cast into the concrete. The difficulty, and this was one of the learnings from the early Stonefields project, was that this rod really needs to be perfectly placed, because it ends up sitting between studs and a wall plate. So the bearing plate that then sits over the top of it, obviously at the next level up, but the bearing plate that would sit over the top of it has to fit between the two studs. So in this orientation, the rod needs to be fairly accurate, and then out of plane it obviously also needs to be fairly accurate, because if the bearing plate sits over the top, if that rod's not centered, then the bearing plate would either clash with the interior lining or the exterior wall cladding. And so placement of these anchors, cast in anchors, is quite critical. And so to avoid that, or to avoid potential issues when they aren't exactly right, a common detail now is to actually have a steel plate that has steel attached to the bottom of it that gets cast into the concrete, and to that steel plate we then weld a steel starter block. So we've got steel starter blocks that normally allow you to connect a rod to steel beams. That steel starter block gets welded onto the actual cast in plate, and that is obviously a lot easier to get exactly right, because at that stage the concrete's done, we know where the edges are, and we can measure out exactly where that steel block goes, so that rod actually sits nice and centered in both orientations. So why wood? We've talked a fair bit about 3604 and 3603 in this presentation. Obviously, timber has a lot of benefits in terms of sustainability, in terms of what we're used to for residential construction, our level 1 building importance, level 1 and 2 buildings, and we're seeing an interest in progressing that into multi-storey design, both in terms of the update to 3604, but also in terms of developers and engineers, end users wanting multi-storey designs done in timber, whether it's like timber frame, CLT, or any other mass timber type design, but nonetheless it's wood. One of the key things to remember, and that was really the point of the presentation today, is that just because 3604 has a light timber frame and we're now moving into larger timber buildings, multi-storey design with light timber frame, that are designed to, or they should be designed to 3603 rather than using the 3604 method. And that's connector design, as I talked about, in terms of using the right characteristic capacities or the right design capacity information for your joints. Also looking at bracing, making sure that we actually get our bracing right, and we consider stiffness, not just the strength, so not just plugging standard bracing designs into 3+ storey buildings, and using timber or different engineered wood products rather in their right application to actually come up with a cost-effective solution for the end user, and that will hopefully help encourage much greater uptake of these timber buildings. So that sums up or brings up the end of my presentation. There's a little QR code up on the screen. If you scan that, and appreciate that you're looking at your own screen, so it might be a little bit hard to get your phone to pick this up, but if you get your phone to scan that QR code, that brings up my contact details. So if you have got any questions, then please do reach out, and I can certainly provide you with more detail. And I also believe that we should have a little bit of time left now for some questions and hopefully answers to those. Thank you.
Thank you very much, Daniel. That was really very thorough and informative to set the differences between the connectors according to 3603 and 3604 and the characteristic strengths calculations. That's really very good information to learn, and also to describe bracing, holding down bolts and connectors. That's also very good information to learn about. And just wondering, like, if it is possible, maybe others would get the benefit from that. If your presentation PDF can accompany the recording on the website, that will be good to follow, just in case they need a reference to look after. That's up to you, of course. Now we are moving to questions and answers. My colleague, Daniel Moroder, will facilitate the questions and answers. And Daniel, please, it's all yours.
Thanks, Namir. And I also would like to join Namir in thanking Daniel for this presentation. You covered a lot of terrain, and I think you made some ingenious think. I hope you made some ingenious think about using 3604 versus 3603 with this larger timber structures. Before we go into the question, there's a comment from Shane which I want to share. Obviously, the new standard NZS AS7020.1 is available. If you go onto the SNZ, the Standards New Zealand webpage, there is a version with and one without the Australian standard. So the New Zealand standard is an appendix to the Australian standard. So you might have to buy the full copy of the Australian standard to read it with the appendix. If you do have that copy ready, just buy the appendix. So just a quick one on that. Perfect. Then let's go jump to the questions. There's one from Michael who asks if Simpson Strong-Tie provides the stiffness values of the different fasteners.
Yeah, and I sort of touched on that in the presentation, but yes, we do provide some of that information. There's for each of the products on our website, there's a little tab that says technical data and docs. On that, you'll find test reports, and those test reports quite often have, for the hold down connectors, will have loads at a given displacement. So from that, you can work backwards what the stiffness is. We're also looking at, we're finalising a mass timber catalogue at the moment that will actually have the stiffness values published in it. The difficulty that we had with that was determining what we actually wanted to publish. What we are going to publish is a simple relationship between load and deflection from test data, which gives you, similar to the whole presentation, around 3604 versus 3603 and how we analyze test data. The Brands Mid-Rise Guide talks about KECR, which is a European design factor, stiffness factor. That has a different analysis method. So if you analyze your test data to that, you actually get a slightly different result compared to just a straightforward load versus displacement. So what we're going to publish is a load versus displacement, given that KECR isn't actually a factor that's referenced in our standard directly.
Thank you. My take would be any data is better than no data, because currently there isn't much information available. So thanks for that. The next question is, it's about the competitor's product, but you might be able to answer. So all multi-characteristic capacity is normally referring to 3604 requirements. Will this be acceptable to use, like, would it be acceptable to use this characteristic data for any buildings outside 3604, or is any additional reduction factor required?
Yeah, and it's not a simple reduction factor. That's why I say it's really the analysis of the test data. And I think there was a question further down that asked about the test data too. I might come back to it, but I can't comment on what the analysis was. I suspect that the results that, or the capacities that MITEC publish are based on BOINZ EM1, given that the focus for light timber frame obviously traditionally has been on 3604 type buildings. And that's exactly my point, that I think we just need to be careful that we're using the right information as we push timber into applications where traditionally we haven't seen them, and that, you know, traditionally light timber frame has been in 3604 and not much outside of that. So yeah, I can't give you a black and white answer to that because I don't know what the analysis is, but my gut feel would be that MITEC would publish BOINZ EM1 calculated data.
Yeah, when in doubt, I recommend ask the supplier. They normally can provide you with an answer. There's a question regarding the taller builders. You showed some slides on that, and the question is, do the rigid body rotations of the upper floors lead to damage? When comparing interstory drifts to the code drifts of, say, 2.5%, should we care about the rigid rotation component that doesn't physically load the sheeting wall elements?
Yeah, probably not really a question I want to answer. I guess we don't, you know, and I'm not sure that the intention of that question is really around using different materials, whether it's a mix of, so if you're mixing CLT with a light timber frame anchor tie down system, those two components, absolutely, you'd want to carefully consider the impact of one against the other. I guess if you're designing taller buildings with a rod system, with the strong rod system running all the way up the building, then obviously performance at each floor level is going to be fairly predictable and identical rather than highly differential.
Correct. And I think my answer would be, it's not just about the structural element, it's the non-structural elements which need to go for the right and need to be protected. I encourage people who are interested to look at the BOINZ light timber framing guideline, which addresses some of this. There's another another interesting question is about if you could comment on how to consider perpendicular to grain deformation at the compression cord location in multi-story timber buildings, and if you are aware of any brackets or devices to reduce these effects.
In terms of brackets or devices, no, there isn't. And I guess this ties into why I talked about the different engineered timber products that are in the market. Obviously with particularly LVL, which is quite often used in framing, you do get different material properties to sawn timber. And so your plates or anything perpendicular to grain, you can design, or you can reduce the amount of deformation you get perp to grain by using different materials. Similarly with taller, and this isn't so much 3 or 4 story buildings, but when you're getting into 6 to 8 story overseas, the flooring quite often is hung on the inside of your wall frame to actually reduce the amount of perpendicular to grain exposure that we have from floor joists that would ordinarily sit between the wall panels.
Yeah, one way could be to simply bypass the floors or put steel elements in. Correct. As an idea. Can you comment on the stiffness compatibility between the strong ties and the other tension load paths that exist in the ply OSB sheeting panels and studs? And in the tests which Simpson Strong-Tie has carried out, has the load in a strong tie been measured, and does it stack up against simple analysis assumptions in the strong rod?
Yeah, I mean the rods obviously. So these rods go up to a 50 mil diameter. And so the tensile loads that you can pick up through the rods are significantly higher than what you'd ever get in any panel. So the short answer is that there is no, your tensile load absolutely goes through the rod because it has a much higher capacity than what any sheathing or structural element would have around it. And as far as the question around testing or whether it was just analysis, Simpson does have a 3-story high test facility as our own test facility. And so yes, the results that we publish, or the capacities that we publish, have come out of tests where it is tested as full scale 3-story. So those if there was issues around stiffness interaction between the rods and other elements, they would be taken into consideration given the results are actually from test results over full scale 3-story.
Thank you, Dan. There's another question which you might have answered, but I think it's worth bringing it up again. The question is the significant difference between 3603 and 3604 hold down characteristic capacity. Is it mainly due to stiffness, or is there more behind it?
It's a mix, and I guess that's what came out in the presentation, right? So that there are additional factors that get applied in 1649 that aren't applied in brands EM1, and that gives you a sort of 1.5 factor. If you look at the stiffness can have an impact on that, but it doesn't always. And the DTT2 example that I had in the presentation actually was one where it wasn't governed by stiffness, but it was simply the pure difference between 3603 versus 3604. Analysis.
Thank you. We are running slowly out of time, so I probably condensed some of the questions. There's a question about, is there any design methodology for the Strong-Tie connection into the concrete foundation across different concrete grades? Do you provide some methodology or guidance on that?
Short answer is no. I guess the design is your design. So what we provide you with is sizing, and this is the cast and anchors are by and large now really being done as specific engineering design anyway, rather than using our cast and anchors. But even our cast and anchors, you'd still need to check the actual resistance against the pre-attached washer on the cast and rod.
Mm-hmm. Yeah, thank you. What if the shear walls or tie rods are staggered between stories due to the wall layout on each level? Do you have any comment on this? So I guess the question is, what if the walls are essentially not aligned up the building?
Yeah, I'm not quite sure what by stack. So if one wall doesn't sit directly over the top of the other, it becomes incredibly difficult because your rod obviously is no longer continuous. So you're essentially designing a cantilever, some form of cantilevered floor to pick up the load from the rod coming down from above. On the end of the cantilever, and then tying back that down to level. So no, that the whole intention of these systems, these rod systems, anchor tie down systems, is to be continuous and aligned over the height of the building.
Yeah, I think the question is, or the answer would be, make sure the load pass exists, and a staggered shear wall is not a good shear wall. This would be my answer to that. Anne is saying, thanks for the excellent presentation. And she's wondering if there's more CLT connections coming into the New Zealand market. I think you mentioned mass timber catalog.
Yeah, correct. So absolutely, Simpson is looking at that. There's a whole lot of other suppliers that are starting to enter the market. So obviously there's already a couple of suppliers in the market. Simpson had a look at it, or we started bringing some of these components in about a year ago. Our focus was really on picking the components that we thought were most relevant and having those in stock in New Zealand. And like I say, there's a pending publication of that mass timber catalogue coming up, which will have a couple of new products in it to add to the range. But there are other suppliers coming onto the market as well. So absolutely, there's going to be a big increase in CLT type connectors. Interesting question for a rod system, but yes.
Thank you. And I'm gonna ask you the last question for today. And the question is, does the use of Simpson Strong-Tie rods have effect upon the stiffness of the building in general, and particular vertical wall bracing? However, also in horizontal diaphragm behaviors. And the follow-up question is, could the strong rods actually be used horizontally to stiffen the diaphragms?
So the first question is yes, absolutely. Overall building stiffness, and that's the stiffness of the rod itself will have an impact, as will settlement. So we provide information around displacements of the devices themselves and bearing plates, and obviously that the rods themselves will have a stiffness, or we provide stiffness information. So absolutely in the vertical. In terms of could they be used in the horizontal, I've seen them used in a couple of very alternative applications. One was in a building where, similar to the question before, where the walls weren't lined up, and it was only a residential building, but they were used as hold downs to grab the end of a long cantilever with a short backspan, and the rods were used to grab the end of that backspan. Obviously, in terms of movement, little benefit in the take-up devices, because they wouldn't really settle or wouldn't take up any of the shrinkage, because the devices would never go into a no-load situation. Similar with the horizontal, the ratcheting take-up devices would probably be tricky to use in the horizontal, because they wouldn't necessarily ratchet through over the length of the diaphragm. But the screw jack type devices, yes, you could potentially use them in that orientation. Not something that we've got information on. Yeah,
and my take would be, I think you could use the tie rod as a tension cord, but when it goes into compression, it doesn't really work well. And the stiffness of a diaphragm is mostly coming from the panels and the nailing of the panels. Well, there's a handful of questions left. I think we leave them for now. Thank you, Dan, for your excellent presentation. I think it has obviously created a lot of interest, and I'm sure there will be more questions raised moving forward. And Dan will also give a similar presentation in the upcoming CISO TDS Roadshow in March. It will be publicized very soon. There will be another occasion to ask Dan more questions. Well, thanks everyone. Thanks Dan, thanks Namir and the team at Engineering New Zealand, and everyone for listening in. And I see you at the next webinar. Thank you and bye-bye.